Hi, this is the part 2 of the video for entropy. So in part 1, we just looked at the introduction of entropy as a new state function, hopefully very relevant in the description of the second law of thermodynamics. We are continuing the discussion here. Let me make some space for the new content that we'll be discussing. Now, I want us to be careful here as we are working with this new expression. So let me start out with a counterexample of when this doesn't work. So a good source of counterexample is something we looked at earlier, free expansion of a gas. It's a non-quasi-static, irreversible process, and it's a good source of counterexample because so much of the things we do relies on the assumption that what we are working with is quasi-static and reversible. So let me draw the PV diagram of this free expansion here. You start out at some state, some pressure and volume. After the partition is removed, the volume doubles. And as we discussed before, the temperature doesn't change. So that must mean pressure halves. So the state of the gas ends up at somewhere around here. Alright, so that's the change that takes place. I'm not going to draw a path because this is a non-quasi-static process, and drawing a path on the PV diagram implies that there's a path to be drawn. Here there's no path. You just start at A, some moment later you're at B. Now, if you try to naively apply that change of entropy is equal to Q over T, you will naively conclude that change of entropy is zero because there was no heat transfer. In fact, your textbook calls this an adiabatic process, and I never liked that description. And I hope when you hear this description, I hope this sounds wrong to you, because it should not feel like that somehow the state of this gas here, occupying half the volume, is same as the state of the gas here, occupying double the volume. It should not feel like you have gone through a cycle and the total change of entropy was zero. So I hope your intuition tells you that something is wrong here, that this is not correct. So if this isn't correct, what can we do? Well, we can use the fact that we think this entropy thing is a state function, which means the actual path you take shouldn't make a difference. Now here there was no path to take, so let me just draw a path, which is not going to be the free expansion process that took place, but it's a path that I'm using purely for calculation. Let's say we have an isobaric expansion followed by isochoric cooling. Because these are both the steps I have taken in the earlier calculation in part 1. And I can just kind of look up the result, change the variables. Okay, let me do that. So the change of entropy in process 1 is equal to, looking over, it's 3/2 nk natural log of, I need to label the point. Let me call that C, Tc over Ta, plus there's a change of entropy associated with the change in volume, and natural log of volume at C over volume at A. Alright, change in entropy in process 2 is there's no change in volume, just change in temperature. 3/2 nk, the final temperature over the initial temperature. So now let's write down the correct change of entropy. If you look at it carefully, the first two terms actually cancel out. If you factor out 3/2 nk, add these together, then Tb is actually equal to Ta. So the second thing is just a minus of the first thing, so they cancel out. And you are left with the third term, nk, the term that's associated with the change in volume. And volume at C is same as volume at B, so let me write that. Vb over Va, or in this case, natural log of 2. So yes, there is change in entropy. So I like better. That's probably correct. So this is what this comes down to. The expression that we guessed at earlier, apparently it's not universally applicable. Instead, we have to be careful that it's describing reversible processes, or at least the quasi-static processes. You need to have an actual path to integrate over. When you have a big jump, like what free expansion describes, neither this infinitesimal expression or this finite expression applies for those big jump processes. Instead, what you have to do is come up with a quasi-static path like we did and just to calculate the difference for the endpoint using a reversible path. Okay, so this is a bit of a counterexample. I wanted to lead with this because this is a very common mistake that many students in thermodynamics make. All right, let me show you the second and the last example that's sometimes called Clausius inequality. Let me make some space again. So if you've seen this written out before, this is what the inequality looks like. It describes integral over a closed path of this quantity dq over t. And even though that kind of looks like the entropy over there, I'm gonna be careful not to quite say that. Because I want to be careful about how I'm labeling these parameters here. The inequality says this, that that this quantity here is less than or equal to 0. The equal to part is what we have been actually working with already. It applies to when you have only reversible processes going on in your system. So that's what we've been naturally working with. The inequality portion applies to when you have an irreversible process happening. So let me be a bit more concrete. Let's start out with a process, something that's nice and easy to deal with. Carnot cycle. It's nice and easy because any kind of heat transfer happens along an isotherm, and whenever temperature is changing, there's no heat transfer. So with the Carnot cycle, we don't actually have to do any integral, so it makes it nice and easy. And we can quickly verify that the case with the equality holds for the Carnot cycle. In fact, I think that's how we propose the idea of entropy. Along this path here, we got that dq over t, or delta q over t, of qh over th. And along this path here, we got the delta q over t of minding the direction minus ql over tl. And with the relationships we saw in the expression for the efficiency, we knew that those two canceled out, added up to 0. All good. So how do we get the irreversible case? Well, I have to take this nice, reversible, ideal Carnot cycle and somehow make it non-ideal. And we talked about sources of irreversibility before. That is friction or irreversible heat transfer. Friction is a bit complicated, so let's say it's still frictionless. That'll make my job easier. So how I can make this process irreversible is I can make the heat transfer irreversible. So far, without explicitly saying so, the heat transfer here was reversible because the heat transfer was occurring between two things that were at the same temperature. Both the high temperature reservoir and the engine was at temperature TH when the heat transfer was occurring. Now I'm going to say that the thermal reservoir is not at TH. It's at some temperature slightly greater than TH. So this is the temperature of our high temperature thermal reservoir, TH prime. And this is going to make the heat transfer irreversible. And I don't have to stop there. I can make the heat transfer on the lower isotherm also irreversible. Instead of saying that heat transfer is occurring from thermal reservoir at temperature TL, I can say, well, it's actually colder. because that's gonna make the heat transfer occur more quickly. So the waste heat is being expelled into a lower temperature through an irreversible process. Now, if you are wondering how this modification is going to affect this expression here, as long as you are talking about the engine, it actually doesn't affect it at all, because nothing about the engine has changed. And in fact, since the entropy is a state variable, that means reversible, irreversible. If you are coming back to the same state, the total change should still be zero. So this is why I wrote this Clausius's inequality this way. The thing that you are integrating isn't quite the entropy of the system. It's dq, heat transfer into the system, over the temperature of the reservoir. So you can see it here. With the quantities that are going to cause positive change, the temperature of the reservoir is now higher, so the positive terms will be less than what it was before. With the terms that are going to cause negative change, now the temperature is lower, so the magnitude will be greater, it'll be more negative. So when you're done adding it all up, it is going to be negative for this irreversible setup. So this is Clausius's inequality. And this does relate to the third way we will be specifying the second law of thermodynamics. This quantity here, once you realize that you can relate dq to heat transfer relating to the reservoir, then what this integral actually represents is minus change of the entropy of the reservoir. Over one heat engine cycle, the change of the entropy of the heat engine is going to be zero. That's true whether it's a reversible process or irreversible process. That's what, once again, the state function is about. It doesn't matter how you got there, it matters where you are. What Clausius's inequality is saying is for the surrounding, it's not always going to be zero. If that cycle for the engine took place using irreversible processes, then this minus change of entropy of the reservoir is going to be negative, meaning the change of the entropy of the reservoir is going to be positive. And this is the third statement of the second law of thermodynamics, that change in entropy of everything. In chemistry, they like to talk about isolated systems. I'll just say universe is an isolated system. So change in entropy of everything is always greater than or equal to zero for all processes you can imagine. So it's equal to zero if you're dealing with the reversible processes, and it's greater than zero if you had the irreversible process happening somewhere. Okay, so that's everything I have to say about entropy for now. I have one more description of entropy I'd like to give, and one more statement of second law of thermodynamics that's not in your book. Until then, bye.